Whether you're looking to take advantage of multi-core CPU systems or to do distributed computing, today is your lucky day, as the article that we'll be going through will give a great framework for both of these. So join me, Ryan Wienko, as we dig out yet another invaluable gem from the GameDev.net series, this time from the Advanced Programming book. So buckle up and get your compilers ready, because this is Industry Broadcast. I would like to start off today's article by thanking Drew Sikora and John Hatton, as well as everybody else over at GameDev.net, for putting together this great series of books, especially the Advanced Game Programming book, which we'll be reading from today. Today's article is titled Multi-Threaded and Distributed Computing with the Actor Model, and was written by Michael Sikora. For the suitable type of problems in your game, particularly server components, liberal use of the actor model type of architecture should give you near-perfect scaling across multi-core systems. It will also provide a few unexpected side benefits that will decrease your development time and increase your confidence in the reliability of your code compared to other concurrency programming techniques. Pretty lofty promises, I know, but there will be trade-offs, and I will cover those as well. In order to tie the whole article together, I will discuss one specific game programming problem: computer-controlled players. I will take the premise that you are developing a massively multiplayer online game with thousands of computer-controlled players running into each other in world instances. This is a relatively high-level problem that you will solve with parallel execution. The computer player units will not be doing anything particularly interesting, but they will be doing it in parallel, and they will not know or care what machine or thread they are on. Many developers are accustomed to searching out much smaller, simpler problems to run in parallel. These include physics calculations, pathfinding problems, and so on. While it's great to run these tasks in parallel, it does not always lead to a constant use of the available CPU resources over time. However, using the practical actor-like model outlined herein and breaking the problems into more naturally recurrent problems will lead to better CPU resource utilization. That is what I will show with a computer-controlled player example. Multi-threaded and distributed computing. Brothers or second cousins? First, I'll look at the similarities and differences between multi-threaded and distributed computing. Are they closely related, or just somewhat related? Most developers immediately recognize the obvious similarities between these two concepts, namely that they do some form of processing in parallel. However, they are also similar in a few other respects. Parallel execution. This is the definitive common feature. Both multi-threaded and distributed computing are based around this feature. Shared memory. Most multi-core CPUs use shared memory that each core can access. Distributed computing rarely relies on using the same memory resource. Instead, it relies on distributed copies of the data used in calculations. There is, however, one extremely common system setup involving shared memory for distributed computing. Many distributed systems use a single database server, which provides the definitive state of a game system to the rest of the non-database servers in real time. Communication latency. It is easy to dismiss the latency consideration of sending a signal between multiple threads of execution, since they are directly comparable to the cost of copying the information in memory itself. In contrast, the latency between two computers on a network may be longer than the time it takes to compute the entire task itself. Communication bandwidth. Again, sharing information across threads is similar to sharing information within a thread, copies of information or shared memory. Unfortunately, this is not the case with distributed computing. The amount of information that can be passed between computers is more limited, with the time required to transfer large amounts of information being unacceptable. You might think that the communication bandwidth and latency issues with distributed computing are difficult to work around. In practice, however, server clusters on a private network often have reasonably low latency and high bandwidth. For this article, I'll assume that you are planning to run your system on a reasonably fast, high-speed network. That means that the internet is generally out of the question unless carefully planned out. With that in mind, you can see that executing multiple tasks in parallel is, for the most part, similar with regards to both multi-threaded and distributed computing. Now I'll move on to how you abstract away the differences so that you can work with one model instead of two. This is where you get these side benefits with regard to development times and reliability. By working against one model, you can effectively test both ways of computing at the same time, making it easier to be confident in the code as a whole. Also, you have one common model, you can focus on the important thing, and that's distributing tasks across all types of computing systems and resources available in your game. The actor model. Distributed computing is not a new concept, so there are a lot of ideas out there already for how to best use a multi-computer system. The one I'll discuss here is the actor model. The actor model is a message-passing system where the message sender and receivers are known as actors. Actors do all of the work in the system, and they do all the work in parallel by design. You may not have heard of the actor model before, so I'll take a quick tour of its principal concepts before building a practical implementation. The first thing to know about the actor model is that communication between parallel processes is driven by messaging. It is likely that you have come across various message-passing systems before. Event-driven programming is generally message-based, so is most network programming. However, you may not have seen a general parallel computing model where all communication is based on the concept of message passing. There are a few important differences. The key difference is that message passing in the actor model is asynchronous. Practical actor model implementation do not usually guarantee any form of message ordering. Asynchronous message passing is a requirement because actors do not automatically block, i.e. stop executing when they send or receive messages. Now comes the most important part of the actor model. You guessed it, the actors. Actors act, pardon the pun, like tasks or jobs do when run by a scheduler. Actors run independently of other actors or systems, usually continuously. An actor can receive messages, take actions, including creating more actors, send messages, and continue to do computations. Often, each actor has an address that can be used to route messages to the actor, used in conjunction with an address space. The actual implementation details of messaging routing can vary. The message routing mechanism is simply implied. Message routing aside, the key is that in a system of actors, the primary way for actors to communicate with each other is through asynchronous message passing. Be aware that this is a very general definition of the actor model. It has been widely extended and written about since the introduction in the 1970s. There are even actor-oriented languages, interesting enough, but not very relevant to game development, at least not yet. Although I will not be implementing a full-out actor model in this article, it is the inspiration for the simplified model I will implement. There has been renewed interest in the field because of the wide availability of commodity multi-core CPUs and high bandwidth interconnects, so what was once old has become new again. So, when to apply this model? So what type of problems should you consider the actor model for over other forms of concurrency programming? Generally speaking, there are a few questions you can ask yourself when considering a specific solution you want to run in parallel. First, do you need to do parallel processing on different machines in real time? Second, do you need to do parallel processing on different threads in real time? Third, do you need to do seamless parallel processing on a local machine and other machines? Fourth, do you need dynamic load balancing for a series of machines? And lastly, do you have a high-speed network connecting the machine involved in the system? If you answered yes to any of these, you should take a good hard look at a message passing design. Generally, the one red flag warning for using the actor model is if your system is extremely memory restrained. This would prevent you from breaking up your problems in such a way that each actor has enough information to do continuous processing, but little enough that the sum total does not blow your memory budget. For example, assume you adopt an actor model design for concurrently running your computer-controlled characters. I'm also going to assume that your game is running on a console device with notoriously harsh memory limitations, and that you have a few dozen computer players to use at a single time. If they all need to cache, say 10 megabytes of game state data so that they can continue to make decisions concurrently, they will quickly eat up your entire memory budget. Is this a dead end? Not necessarily. If you plan carefully from the start and identify what information actually needs to be shared, you can distribute that information evenly among your actors and then let them transmit the information through messages on a needed basis. Interestingly, this is the way that some researchers originally approached the model, under the assumption that you could rapidly retransmit the messages instead of storing information in each actor. This gave memory savings at the cost of CPU performance. It is ironic that in this article I advocate the opposite: spend your memory to make local copies of information for each actor if you can afford it, so that you can avoid resource contention issues and build multi-threaded and distributed computing solutions with one codebase. To further expound on the virtues of the actor model, say that during the course of development the design gets tweaked, and now you want to have hundreds of computer players in multiplayer matches. The question arises as how you will run all of these players on the host machine, assuming typical client-server architecture. Well, if you have been programming by the actor model from the start, it should take only a couple of hours to get your system distributed on the computer players across multiple console machines involved in the multiplayer game. In practice, it is easy to see how server-side development can benefit from sticking to the actor model as an architecture for parallel task execution. Once you can get decent scaling, it is often cheaper to add more machines than it is to invest developer time into churning out marginally more efficient code. With server-side development, you can also ship with inefficient but correct code and just use more machines per game server instance. Post-ship, if your new game is booming, particularly true for MMO subscription games, you can work on using fewer machines with more efficient code and saving money, which is something managers love to hear. Tell them that you'll be able to ship on time and with the option to reduce their ongoing costs, and you might just get a raise. For client-side computing, it is somewhat more difficult to see the applications. This is particularly true where memory is limited but can be shared. In this situation, most applications of the actor model can be found where multiple systems will be connected for multiplayer matches. You can distribute computer players, physics calculations, and so on among the available machines. If you are worried about a way of cheating by hacking, then you might have to have each actor replicated on 2 different machines so the results can be compared. In contrast to some consoles, most PCs are shipping with a lot of memory these days, so be sure to take advantage of it by applying the actor model where it makes sense. Implementation details. For this modified actor model framework, you are looking for a scalable parallel execution system that fits typical game programming problems. The one significant deviation that I will make in regards to the typical actor model implementation is the way that the actor passes messages around. With the goal of simplifying the example framework as much as possible, each actor will route his messages directly to the desired recipient actor through a single intermediary that handles the synchronization, threading, and network details. This intermediary will form a binary relationship between the 2 actors that wish to communicate. This is the simplified model, which you can use for threading multi-threaded and distributed computing as the same parallel execution system by way of an actor-like model. As you can see, the simplified models have different message passing implementations for messages passed between threads. For example, server to thread binary message passenger to client, and between computers, that's server to thread binary messaging passer to the client. I still have not yet taken care of all the details regarding the creation of these message passers and hooking them up to the respective client and server components. These development details depend on what exactly the actor objects will be doing. Let's first talk about the roles and responsibilities that each one of these classes plays in solving these problems. The actor. This is the computation workhorse object. It fulfills the normal actor requirements by asynchronously passing and receiving messages, as well as executing in parallel with other actors. You may have any number of these in your system, and they may be executing on separate threads or separate computers. It does not matter since the message passer takes care of the communication details. Message passer. This is what makes the system easy to work with. Regardless of how you ultimately implement the message passing mechanism, the message passer interface promises to fulfill these three requirements. First, to accept messages from one or more other objects. These messages will be held for the server/client actor to retrieve at the client's convenience. Second, to send messages to one or more other objects. If the message can't be sent, it is held and sent at the earliest possible opportunity. And lastly, to completely encapsulate the details of the message passing. This is what makes it possible to dynamically take advantage of both multiple threads and multiple systems for generic parallel execution. Both of the realized classes for message passing, Thread Binary Message Passer and Network Binary Message Passer, fulfill each of these three requirements. The first two requirements, receiving and sending messages, are fulfilled by each by maintaining two queues. The first queue is for incoming received messages, and the second queue is for outgoing or sent messages. Incoming messages are saved until the actor retrieves them, at which point they are removed from the queue. Outgoing messages are stored until they can be passed to the other actor or to some intermediate object, which will ensure the message reaches the intended recipient actor. The final requirement is fulfilled uniquely by each realized interface. Since I will be using TCP/IP for these network connections, I will actually have two binary message passer realizations, a server and a client. The server will open a port on the host machine and wait for the client to connect, while the client will simply attempt to connect upon creation. That is the only notable difference. Once both are created, they will behave in the same way through their shared interface. And that's it for today's article, although I would like to mention that this is only half of the article as read in the GameDev.net Advanced Programming book. If you'd like to purchase this or one of the many other invaluable books in the GameDev.net series, simply head over to IndustryBroadcast.com and look into the post associated with this audio article. So that's it for me. I hope you enjoyed today's piece, and remind you, if you'd like to have more of the collective insight of the gaming industry brought to your ears, to head over to IndustryBroadcast.com.